So I'm going to start recording today. We're going over the last little bit of stuff that's going to be in our unit on thermochemistry. So there's like three main topics, like one new definition introduction, and then two ways of using it, stoichiometry and enthalpy. Oh, and you know what? While I'm kind of doing this, I'm going to post the actual the stuff to our class list. So hold on 1 second so I can do that. But in short, it's also the last of new content before we get to next week's exam. So next week's exam is a week from today. As a result of that, we are not going to have actual class on a week from today. Just like our previous test, we'll have all day to do the test. I'll set aside some time for you to be in office hours, which basically means I'll be here and I'll be available to answer questions, but I won't have a prepared lecture or slides or anything. And then as we go into class on Tuesday, I'll have some review work that we can sort of work on and get ourselves prepared for. But we're going to focus on this last new bit of content for today. And then we'll go from there. Just about there to add the presentation. Okay, so let's go to share screen, and I'm going to share my PowerPoint. And this is my daughter. She's very silly, very smart. Are you so smart?
So I just I did give him a science picture.
Yeah, she gave me a science picture, which is up there on my wall. It's really cool. I'll show you guys maybe in class. But I got a good class for you. You want to do that? Okay, thank you.
But I want to show them what I learned.
Okay. Maybe after. That sounds like a great idea. Okay, let's get going. She's 5. There we go. Okay, so class for today, we're going to go under heat under constant pressure, which is going to be our introduction to enthalpy. Then heat as we see it coming out in reactions, and then Hess's law, which is a way to use that information to our advantage, really. Some of the important dates coming up tomorrow. Tomorrow's a very important day. Tomorrow's the last day that you can drop a class with a grade of W. If you choose to drop the class anytime after tomorrow, basically if you go on with the class any day after tomorrow, you're committing to a grade in this class that is either the grade you end up doing or a WF to your withdrawal. So please, if you have to make a decision, tomorrow is the last day that you have to make that decision. Our extra credit is due on Friday. Our homework is due on Sunday. And exam 2 is on Thursday next week. And then also not listed here, but currently open is the latest quiz. That is open until 2 o'clock tomorrow. Please make sure you complete it before then. I sent out an email last night telling you what sort of things you can expect. So enthalpy. Enthalpy is it's a word that we give to heat under constant pressure. So under constant pressure means that we're not constantly applying pressure. It just means that the pressure that the system is subjected to is not changing. So if there is heat currently in this cup of coffee that is being emanated throughout the room. And I can just look at the heat that's being exchanged because the pressure is not changing between what's in this cup and what's outside this cup. It's a constant pressure situation. So like a candle burning or a reaction going on in a beaker, things that are open to the air are sort of thought of as constant pressure situations. So enthalpy, when it gets the symbol H, represents the amount of energy that gets exchanged as a result of heat, not work. So just heat, no W. And that's because under constant pressure, we're not having a change in volume. So I'm going to derive where this comes from. And basically the definition of it is this. It's the total energy of the system plus the product of pressure and volume. So energy is the total energy, the sum of heat and work, Q and W. And if we're going to look at the change in these things, it's the change in enthalpy is equal to the change in energy plus the pressure, which is constant, times the change in volume. So if I exchange Q and W, for E, is total energy, sum of heat and work, these two things. Now I've got this expression. And if I realize that work is negative P times delta V, then I get this expression, delta H is equal to Q plus W minus W, which means that delta H is equal to heat. So that's the derivation of it. Basically, how we arrive at how this definition helps us to arrive at the idea that, yeah, we're just talking about heat, we're not talking about interchanging work. And this little sub P right here just means Q at constant pressure. If pressure is changing, it's a different story outside of the scope of this class. So there are endothermic and exothermic processes through which we learn a lot through enthalpy. So one of the ones you'd be aware of is something that's exothermic, something that produces heat like the burning of natural gas. So that's a system that's losing heat. Okay, so the natural gas is giving up its energy in the form of heat. So the system is losing heat. Q is negative in that case. It's a product in that reaction. And if Q is negative, that means H is negative. Right? So in those cases, when delta H is negative, we're talking about a loss of energy or something that is exothermic. The opposite would be something like this chemical cold pack, and all those things that you sort of like crunch up and then you put on something that needs to be cooled. And in that case, what it's doing is it's taking energy for its reaction to go. So it feels cold to the touch. The system is gaining heat. It's taking in heat energy, and so it feels cold when it's gaining, which means heat's a reactant. And in that case, Q is positive, and delta H is positive as well. So we can do stoichiometry with this, which is basically means we can quantify it. So the delta H of a reaction is often referred to as the heat of a reaction, how much heat is given off as a result of a reaction, or the enthalpy of a reaction. So we have the ability to look at, those things are identical. There's two different words. We have the ability to look at those. So let's imagine we've got this reaction right here. This is propane, used in a lot of cookers. It reacts in air to make carbon dioxide and water, and give off this much heat, 2,044 kilojoules. Because it's negative, what that means is that in every reaction where 1 mole of this reacts with 5 moles of that, 2,044 kilojoules are given off, and it's done so as a product. Because this is negative, it's a product in this reaction. So it's right there on the right-hand side. And we can quantify the total amount of heat. It's not a giant surprise. If I burn a little bit of propane, I get a little bit of heat. If I burn a lot of propane, I get a lot of heat. So that kind of intuitively makes sense, but we can put the numbers behind it. So this is one of the problems that I had given you guys prior to class. Hopefully you had a chance to look at it. You had 1.5 kilograms of propane. And it's going to combust with excess oxygen. How much heat do we get? Okay, well, there's our reaction. How do we get to an answer? Well, we're going to use basic stoichiometry, things we've done all semester long. So we're going to go from kilograms to grams, grams to moles. And then for every mole of this that gets consumed, that's so many joules are being released. I've put the units in, but I've left everything else blank. And that's because I want to make sure that the units are canceled out. So when I put the numbers in, 1.5 kilograms, every kilogram is 10 to the third grams, 41.08 grams to a mole, and every mole ends up releasing 2,044 joules. So there's a negative sign there. And when I do this to 3 significant figures, this rounds to 74,600 joules, or I could say 74.6 kilojoules. And actually, that should be kilojoules here. So that J should be okay. Now that I'm looking at it again. That'll be fixed when this goes up. That should be okay. If I wanted to switch it up and use oxygen, oxygen's got this neat fire right there in front of its thing. So how does that change things? So if I've got 1.5 kilograms of oxygen and it reacts with excess propane, then my setup is the same. I'm just changing the units of what I'm doing from oxygen, from propane to oxygen. And so I plug these things in here. And what I end up getting is negative 19,163 because there's a 5 times in the box. So for every 5 moles of oxygen that end up reacting, 2,044 joules end up reacting. And that's the place where we'll end up seeing these. So basically it's what we kind of had before, changing this bottom number here, changing this number 5, we'll get this much molar number, and that's the number for kilojoules that number coming out. Again, this should be okay there. Just to check. So that is how we would work those two stoichiometry problems, and they all work about the same way. Right? Your book gives you a couple of examples. I think your homework has a couple of examples. You can expect 1 or 2 of these on your quiz. So there's lots of different ways that you can. Now, coffee cup calibration. This is kind of a neat thing. I'm actually doing some kitchen experiments with this now. A coffee cup calorimeter is something that measures a enthalpy change for a chemical reaction in solution, and it literally uses 2 styrofoam cups, where it gets the name coffee cup. And this is a surprisingly good way to keep track of energy, because this is a good enough insulator that you don't end up losing a whole lot of heat. So, as a really good insulator, we can run a chemical reaction on the inside and keep track of how much energy is being given off by a change in the reaction solution. So, remember, the Q of a solution is equal to its mass times its specific heat times its change in temperature. And the Q of a solution plus the Q of the reaction is equal to 0. That's first law. So however much heat is given off by the reaction is gained by the solution. And so Q of the solution is equal to the negative of the Q of the reaction. That's the only way that they can add up and be 0. We saw this before when we were doing our heat transfers. A piece of metal goes into some water and heats up. So we want to see what's happening. So when 50 mils of a 0.1 molar silver nitrate solution is combined with 50 mils of 0.1 molar hydrochloric acid solution in a coffee cup calorimeter, the temperature goes from 23.4 degrees to 24.2 degrees. What's the delta H from reaction? And then there's some additional information here saying use 1 gram per mil as the density of the solution and 4.184 joules per gram degree Celsius as the specific heat capacity. These are dilute-ish solutions, although 0.1 molar is still fairly concentrated to me. But that means that they're going to have a density that's really close to that of traditional water that we're used to seeing. And it's going to have a specific heat that's really close to traditional water. So, recognizing that my Q of solution is equal to my mass times my specific heat times my final initial temperature, I need to make sure I have the mass and specific heat. Well, they did give me the specific heat. It's right there. The mass, however, I had 50 mils of one solution, 50 mils of the other solution. I add them together, I have 100 mils of total solution, which has a density of 1 gram per mil. So if I have that density and this volume, this must be my number in the grams. So I can take that and plug it in. 100 grams times this specific heat times this change in temperature is going to give me this number, 338.994 joules. So that's how many joules we got. The enthalpy, however, is going to be in like a joules per mole. So how many moles did I have in that? Well, it's a 1-to-1 mole ratio. So this is stoichiometric. There's no limiting reagents here. I have enough information to get moles on both of these, but they're both, it's balanced as a 1-to-1, so either one will work. So I can figure out how many moles of silver nitrate I have, so 0.1 molar times 0.05, that's how many moles of it I have. So if I take my heat and I divide it by the number of moles, then I end up getting this on a joules per mole basis. And so I convert it to kilojoules per mole, write numbers in figures, and I get down to negative 67.8 kilojoules per mole. This negative pops up because this is my Q of solution, which is equal to my negative Q of reaction. So I end up multiplying by -1 to get my Q of reaction, which is my delta H of reaction, and so this becomes 0. So this ends up giving off. There are some situations, not many, where you can put something into water and the water cools down as a result. So that would be a place where this would actually have a positive. Questions on that before I move on? Okay, there's one more important topic, and this is really just the one more thing, because this chapter had one topic that we leave out, and that is because it's really better to cover in the science. And so what we're going to look at here is what's called Hess's law. And so Hess's law is a way to recognize that if we change something about a reaction, the delta H for it changes as well. So we saw that in some of our previous examples where if we had a certain reaction going forward and I had more of one reactant or less of one reactant, I would have more heat or less heat generated. Okay? So this is an emission of that. So if I have a chemical reaction and I multiply it by some factor that is double the number of moles of everything going through, then my delta H gets doubled as well. So it looks like this. If I've got some reaction that looks like A plus 2B goes to C, I've got some delta H. And if I double everything, 2A plus 4B goes to 2C, then it's double delta H. So if I double everything in here, basically use twice as much, and generate twice as much heat, or require twice as much heat if it's under. So that's the first bit of Hess's law. The second bit of Hess's law says that if we reverse this chemical reaction, then we change the sign. So if A plus 2B is H1, delta H1, reversing it, C goes to A plus 2C. It's breaking up into these two. Is going to be negative delta H. Okay? So if it's going to be one sign going forward, then it's the opposite sign going backwards. So if this, for whatever reason, if this is exothermic, then the reverse reaction is the endothermic. So if this gives off energy as a product, reversing it means that energy is not. All right, the last one that we have is this one, which is the one that tends to cause the most trouble for students. And this is the one that we're going to, we're going to do an example that uses this one, and you'll see where it takes us. So there's a chemical reaction that can be represented by a series of steps, and the overall chemical reaction, the sum of them, has a delta H that is equal to the sum of each step. So for example, if I have A plus 2B going to C and C going to 2D as two separate reactions, as two separate steps, if I add these together, C will cancel out because it's on both sides of this arrow. My net reaction is A plus 2B goes to 2D. So my delta H of reaction is the sum of these. So individually, they each have a delta H. If I'm adding them together, then the new reaction is the sum of those. All right, so here's an example of this. Find the delta H for this reaction. N2O plus NO2 goes to 3NO. So I want this to be my net reaction. And I'm given this information here. So I'm told that this reaction, 2NO plus O2 goes to 2NO2, has this much energy, so negative 113.1. N2 plus O2 goes to 2NO, and that energy has positive 182.6 associated. And in this reaction, 2N2O goes to 2N2 plus O2, and that has negative 162.2 associated. So it's using the information for reactions we know about to get a reaction we don't know about. That's basically what this is. This is kind of like something we can use to model. So we can model reactions we haven't done by using information from the reaction. All right, so let's see how this plays out. How do I turn these three reactions using those three rules we just used into this one right here? The first thing I always do is make sure that everything is on the correct side. So in the reaction I'm trying to get to, NO2, this is on the reactant side. Here, it's on the product side. Is it in this second one? No. Is it in this bottom one? No. So NO2 needs to be on the other side. So I'm going to move forward here and show you kind of how it plays out. So if I turn this one around, reverse it, that's going to end up reversing the sign, 113.1 to positive 113. Now you might have noticed I've got a 1/2 here, so let's talk about that. I've got 1 and O2 in this reaction. I've got 2 in this one. This is the only place it appears. So that means that I not only have to reverse this, I need to divide it by a factor of 2, or 1/2. So if I multiply everything in here by 1/2, that becomes NO2 goes to NO, and there's 2 of them, plus 1/2 mole of O2. It's a balanced chemical reaction, so nothing's changed in that respect. Yes, we have a fraction right here. We live with it for the moment. But because I multiplied this entire thing by half, that means that I multiply this by half. Yeah. Let's take a look at the second one. N2 and O2, neither of those appear in my net reaction. And they're on the product side of this third reaction. So I think I'm not going to have to reverse either one of these two because that's how these two are applied. And 2NO, well, I've got a total of 3 here, and then 1 from this reaction right here. So I bet I don't have to do anything to this movie. That's going to stay put. This bottom one down here, N2O, that's on the correct side. It's on the left side here from the left side here, so I'm not going to reverse it. But I have 2 of them here, and I only have 1 up here. So I'm probably going to have to divide everything in this one by 2. And when I do, I'm going to end up dividing this by 2. Okay, so now I've got N2O, just got 2 of them, goes to N2, just got 2 of them, plus half a mole of O2, just got 1 of them. Okay. Now, I bet that when I add them together, certain things are going to cancel out. So for example, I've got 1 mole of O2 here on the reactant side, and I've got half a mole and half a mole on the product side. So half plus a half is a whole, cancels with this one. I've got a mole of N2 and a mole of N2, on opposite sides of the arrows. Now, I'm left with NO2, exactly what I want, N2O, exactly what I want, and 1, 2, 3 NOs, exactly what I want. So we'll add those together. That makes this, and I'm going to add together my 3 things here. So half of 113.9 plus half of 180, sorry, plus all of 182.6 minus half of 163.2 will give me 157.6. So that is the amount of energy that's associated with this reaction. Okay. How do you know to switch one of these around or do something? You don't actually intuitively know. There's nothing telling you. All you really need to do is look at where things are in the net reaction you want to get to, and where are they in the reaction you need to get. Things are on the wrong side, flip them. Things are on the wrong amounts, multiply them and divide them. And that's pencil and paper, that's kind of how you do it. That's the end of it. It's much quicker today than we've had in the past, just because there really wasn't a lot left in the chapter. The one area we did not cover in this chapter is an area that deals with, make sure I get the name right, determining enthalpies of reaction from standard enthalpies of formation. That's really more of a second semester topic. So basically, it's much easier for us to go through that way. So we won't end up covering that. So if you're following along in the text, that is section 7.9. All right, so we don't really do that. You should read, however, it's interesting, section 7.10, which talks about energy use in the environment, so that when you are looking at environmental impact reports and stuff like that, and you're trying to figure out where your energy comes from, this tells you a little bit about how every kilowatt hour that you use, every power plant, including the one Duke Energy that supplies all of our power, some of it comes from coal, some of it comes from nuclear, some of it comes from renewable. But all of those things are output, so they're well worth looking into. And that's an interesting part of the chapter too, especially if you're the kind of student, like many of you are, that's interested in this is cool, what's it good for? You can actually figure out how much energy is coming out of a gallon of gasoline. You can start using all this stuff. So that kind of finishes things up for us. Also, I promised I would show you the scientist picture that was drawn from this. This is it. My daughter scientist. All right, let's put that back on the wall of honor. Okay. Questions over anything that we covered today? So if there's no questions, that's it. I'll end the recording, and you guys